So we are going to have this lectures on flow measurements, and we have already done LDV. So we are going to do, the next phase will be to do something which is called hot wire anemometry before we move on to particle image velocimetry. So so we will see first, we'll go step by step, that what are the different flow measurement techniques that are available to us before we jump onto anemometry. So in LDV we already did something. Now we are going to see anemometry and how it actually works. So the materials are compiled from various sources like Oxford Lasers, eFluids, Lavision, Dantec Dynamics, TSI, Virginia Tech Aero, Ocean Engineering, and some of them from my own work as well. So let's start. So as we know that why we measure flow is, we already covered a little bit of this when we did the LDV portion. For example, you can have different types of flow situations. Here you, for example, see a turbulent jet. Let me get the laser pointer. So it's a turbulent jet. This is, for example, a flame. This is from Professor Setijan's work. So this shows a bluff body stabilized flame. This is the nozzle in a gas turbine. So these flows are pretty complicated. And as we already said, sometimes we need both spatial as well as temporal resolutions. And sometimes we need, high sampling rate at a very small location of interest. And that is where the LDV and the anemometry comes in handy. So the flow measurements needed for the physical understanding of reacting and non-reacting flows in applications like gas turbines, aeropropulsion, biomedics, fuel cells, etc. So these are the features which are kind of important. So why we measure flow? This is because flow measurement and flow visualization actually are needed for designing, for improvements, for example, in order to design an efficient combustor, we need to know what is going on inside the combustor, or for aerodynamic designs of planes and shuttles and rockets, and you name what. So all these things comes under the ambit of flow measurement, so to say. So of course, in this list, we have a list of like 4 measurement techniques. We have the pitot tube, we have the hot wire anemometry, we have the particle image velocimetry, and the laser Doppler velocimetry. The laser Doppler velocimetry you already covered in details. Particle image velocimetry is what we are going to do next. So here in this case, we are going to cover the pitot tube and the hot wire anemometry. So the pitot tube, as we know, is the simplest, but it also is the crudest of all the measurements. And PIV is accurate because it is a full field measurement. Now PIV and LDV, as we already said, that these are non-intrusive techniques, but LDV is very good if you want to measure very close to, if you want to have a very high spatial resolution. For example, a few microns, which the PIV may not be always able to get you the velocity at that kind of a resolution. So you have to keep this particular thing in mind when you actually do this. Okay, hot wire anemometry will be similar in terms of the spatiotemporal resolution compared to an LDV, because here also we have a measurement volume kind of, but the principle is completely different, as we would see very shortly in the next few minutes. Okay, so let's start with the pitot tube. So the pitot tube was actually named after Henry Pitot, and it measures the fluid velocity by converting the kinetic energy into potential energy. So how does it do that? There is a hole and then there are side holes. So the velocity comes and you create basically a stagnation point here, and then you measure. So here what you measure is basically the stagnation pressure, and the pressure which is higher than the free stream pressure, and the static pressure, what you measure through the side holes, is then also measured, and the difference of these two pressures is what you get. Okay, so the pressure which is higher than the free stream pressure is called that is the dynamic pressure, and the static pressure is measured by comparing it with the dynamic pressure, and you use a manometer basically to see the difference in pressure between the two. So the construction wise, several small holes are drilled around the outside of the tube, and then there is a central hole which is drilled down the axis. So if you look at it carefully, the outside holes are connected to one side of a device called a pressure transducer, okay? And the central hole is kept separate from the outside holes and is connected to the other side of the transducer, okay? So the transducer, what does it do? It is basically, it can be a manometer, as simple as that. It measures the difference in pressure in the two groups of the tube by measuring the strain. So basically there is a thin element. So if you have a difference in pressure, you induce a certain amount of strain. So by measuring the strain, we can determine that what is the difference in pressure. The pitot static tube is mounted so that the central tube, okay, is always in the direction of travel. That means they are kind of aligned head on. It takes the whole flow head on, and the outside tubes are basically perpendicular to the central tube. So like what you have over here. So these are perpendicular, these are central. Okay. So by converting the resultant differential pressure measurement into a fluid velocity depends on the particular fluid flow regime that the pitot tube is measuring. So if the fluid regimes are incompressible, subsonic, compressible, or supersonic, these are the kind of flow regimes. So this is not like laminar turbulent kind of thing that we are looking at. We are looking at incompressible flow situations. We are looking at subsonic compressible flow, and we are also looking at supersonic flows. So the incompressible flow, if you look at it, so it is for a Mach number which is less than 0.3, so the fluid is virtually incompressible. So for such a fluid, what you can do is that you can apply the Bernoulli's equation, which describes the relationship between the fluid velocity and the pressure along a streamline, and neglecting all the viscous effects. So between the points 1 and 2, so if you go back and see 1 and 2, the streamline, one can write this particular expression. So this is like V1 square by 2g plus P1 by rho g plus H1, etc., etc. Now for the same elevation and for a stagnation point, as you know, for a stagnation point, the velocity is equal to 0. So this velocity now, okay, becomes the P stagnation minus P static divided by the rho multiplied by 2 and the root over of that. So this is what you are going to get when you actually have an incompressible flow. All right, so it is pretty obvious that you are measuring this differential pressure, and because you are measuring this differential pressure, you can infer the velocity, which is basically the square of the differential pressure. That will give you the velocity by simply using the Bernoulli's. Okay. If it is subsonic compressible, that means when the fluid velocity is 30% more than the sonic velocity, in other words, the Mach number is greater than 0.3, the fluid must be treated as compressible. Now, if we do that, if the fluid is treated as compressible, what happens is that now the pitot tube is now exposed to a subsonic compressible flow. That means the Mach number is greater than 0.3 but less than 1. So the fluid is traveling along the streamline that ends on the pitot tube stagnation point is continuously compressed. So previously you did not have this compression effect. Now it is continuously compressed. So we assume that the flow is decelerated and compressed from the free stream straight isentropically, that means adiabatic reversible in nature. Therefore, the fluid pressure relationship for the pitot tube now gets a little bit more complicated. There is now the K, which is 2K divided by K minus 1 divided by P static divided by rho static multiplied by the P stagnation by P static raised to the power of K minus 1 by K minus 1 and the entire root. So K is the ratio of the specific heat at constant pressure to the specific heat at constant volume. Okay. So that is what you get. So this is the velocity expression now, which is a little bit different from the velocity expression that we had earlier. This is just because of the fact that the flow is now decelerated and compressed. That means at the stagnation point. So, and this is valid for subsonic compressible flow. So So the pitot tube can in essence find out the velocities in both the cases. All right. So the advantages are that the pitot tubes are, very simple to construct. You can construct it yourself. All it requires is a central hole, and you need a bunch of side holes, tappings, which are perpendicular to the flow direction. So it is inexpensive and it requires no prior calibration because you are measuring the differential pressure also. It can be easily placed in the flow field, but the disadvantages are quite a bit. It is low accuracy and spatial resolution because you see that, the pitot tube has got a finite dimension. So it is kind of, not very, it's actually a little bit bulky. So the tube also must be aligned with the flow velocity to obtain good results. So it is aligned with the flow velocity. Any misalignment in the yaw, okay, should not exceed a certain degree. Okay, and it is intrusive and it disturbs the flow pattern. So it may not be therefore valid for complex and time varying flow field, or the flow field which has got a lot of structures. So for laminar well behaved flow field, this is not an option per se. I mean, this is an option to go ahead with a pitot tube. Okay. So that is the advantages and disadvantages of a pitot tube. Okay, so of course the pressure transducer, you can use a manometer, you can use the strain gauge type of pressure transducers. All of them are good. The electronics is also very light, so that is an added advantage for this. All right. So now we move on to the case of hot wire anemometry. Now, hot wire anemometry is the most well-known thermal anemometer, and it came before the LDVs, and it measures the fluid velocity by noting the heat that is convected away by the fluid. Now here comes the crunch, that it is actually measuring the fluid velocity by noting the heat that is convected away. So it is not directly measuring the flow velocity. So it uses heat transfer to find out what is going to be the flow velocity. So what is the core of an anemometer? It is the core of an anemometer, hot wire anemometer, is an exposed hot wire that you see right around there, okay, which is either heated up by a constant current or maintained at a constant temperature. The heat that is lost to the fluid by convection is a function of the fluid velocity. This we know from convection heat transfer. The amount of heat that you lose is a function of your Reynolds number. So Reynolds number is a function of your fluid velocity. As a result of that, the heat that is lost to fluid convection is a function of the fluid velocity. So if we can somehow calibrate this, okay, and then you can actually determine what is going to be the velocity of the flow field in which this hot wire anemometer is placed. So how this is done? This is done by measuring the change in wire temperature, either in a constant current mode or the current that is required to keep the temperature, to have a wire temperature. The heat loss is obtained by that, and as a result of that you can measure that what is going to be the flow velocity. Okay, so just by measuring the change in the wire temperature, we can actually, or the current that is required to maintain the constant wire temperature, the heat loss can be obtained, and we can correlate it with the fluid flow velocity. So hot wire anemometry can actually measure all three components. So it can measure one component, two components, or three components, all. So the velocity component like UX, UI, and UZ, this is measured over a helicopter, for example, with 2D and 3D probes. So you can see how the velocities are actually obtained. You can see the velocities are about 25 meters per second, so in that particular range. So no problem that you can do it with a hot wire application. So this is what the anemometer signal looks like. So anemometer provides what we call an analog output. That means it represents the velocity at a point. The velocity information thus is available at any time. Whereas LDA or PIV, they will give you informations, LDA signals and PIV signals are timed. with frame grabbing of illuminated particles. So this is more of a continuous signal. This is more of a signal in which you get the information at certain discrete time snapshots, essentially. Well, of course, this frequency can be very high depending on your lasers and high-speed PIV. So that's why LDV is a little bit more high-speed than PIV, but PIVs are also getting very high-speed these days. So as a result of that, you can get a lot of data within a very short span of time. But unlike an anemometer, which it will be very continuous, so this will give you almost a continuous data. Still, there is an analog to digital conversion, so you do lose a part of the signal depending on how you are sampling, but technically your data is available, so you can sample it as high as you can, whereas in LDA and PIV this is not quite the case. All right, so what does an ideal transducer actually do? So for example, if you look at any measurement principle, what happens is that you have a physical quantity that you try to measure. So you get some signal out which is passed through a transducer, and then this transducer generates an output signal. So if in this case it can be anything, it can be velocity, it can be any other types of signals. So the output signal is proportional to the magnitude of the physical quantity. So it has to respond to the change in the physical quantity. The physical quantity is measured at a point in space. So this is like a point, or whatever is the dimension of that point. So it is exactly not dimensionless either. The output signal represents the input without any frequency distortion. That means there should not be any distortion in how you are actually gathering the data, and there should be low noise on the output signal. So the signal to noise ratio should be quite good so that you can recover the data. Okay, if it is buried in the noise, you cannot actually see what is the exact value. All right, and the transducer should not interfere with the physical process. That means it is not interfering with the physical. That means it's not changing. The act of measurement is not really changing the physical quantity that you are trying to measure, and the output is not influenced by other variables. So the output is not influenced by other variables apart from the physical quantity that you are trying to measure. Okay, so these are the kind of transducer dynamics. So real transducer dynamics is that you have a static transfer function, which is like a calibration curve. The spatial resolution is important because of your finite size of your measurement volume. We also saw that in the case of LDV. The same thing is valid for any measurement. The temporal resolution is its frequency response, that how small a frequency or how large a frequency you can safely measure. It should have a very good signal to noise ratio. The interference effects is very important, coming from other types. Okay, and it normally the multivariate response. That means it not only responds to the variable that you are trying to measure, but all the other variables as well. So that basically convolutes your measurement. So in the case of hot wire anemometry, if you look at it carefully, the hot wire, the anemometer wire, is made of platinum or tungsten. Okay, so this is the wire. If you look at it carefully, so these are two prongs and the wire is held between these two prongs, and this hot wire is made out of platinum or tungsten. So the wire is roughly about 4 to 10 microns in diameter. Okay, so this particular cross section of the wire, okay, the wire is about 1 mm in length. So this length part of the wire is about a mm. So you can see that the measurement volume that it kind of gives you is about 1 mm by about 10 microns. So it is like a very high aspect ratio. So it is 1 mm by about 4 microns. So it's a very slender kind of a stuff. So you can see a practical anemometer over here. This is a tungsten wire, okay, with thin platinum coating. Okay, and here you can see it is 1.5 mm, 25 mm is the length. Okay, and then it is connected to the electronics after that. So the tungsten hot wire sensor and supports this is a practical example. So all available hot wire anemometers have a flat frequency response, so up to about 17 kilohertz at an average velocity of 9.1 meter per second, 30 kilohertz at about 30.5 meter per second, or 50 kilohertz at about 91 meter per second. Okay, So these are the anemometers which are available. Okay, the newer ones might actually do much better than this. It is fragile. That means if you touch this wire, it will break. So thus it is suitable for very clean flows. You cannot actually have a very dirty kind of a flow where there are a lot of particles or fragments which will hit the wire and break it. Okay, because we will see why that thinness of the wire is actually needed. It is a very fragile piece of equipment. That much we know for sure. Okay. So the hot wire type sensor must have actually two characteristics to make it very useful. It should have a high temperature coefficient of resistance and an electrical resistance such that it can be easily heated with an electrical current at practical voltage and current levels. Okay, so that it can be easily heated up within using the current level that our normal power sources can actually supply. Okay, so the tungsten wires that are used are very strong and they have a high temperature coefficient of resistance, which is about 0.004. Okay, however, they cannot be used in high temperatures in many gases because it can get oxidized. So tungsten gets oxidized in very high temperature gases. So platinum has got good oxidation resistance, good temperature coefficient, but it is very weak, particularly at high temperatures. So these are the pros and cons of the different candidates that we can have. But the main part of the sensor is that wire, because that is the wire that is actually exchanging heat with the flow, and that is what will give you the velocity measurements. So it is thin, it is high aspect ratio, and it is usually made out of tungsten and platinum, keeping in mind what kind of flow situations you are dealing with. Okay, so what happens is that sometimes what you have is you can have a platinum hot film. So this is a wire which is coated with a film, and then there is a hollow glass tube or a quartz fiber through which you can cool this wire as well. So this is, for example, a gold plating sensing length. This is a quartz coated with platinum film sensor on a glass rod. So this variation is therefore called hot film anemometry. It's like a wire, but you have a coating. So there is a film which is given on a particular glass or quartz. So this is very useful for velocity measurements in liquid or rugged gas flows, because as you saw, this will not break that easily. The platinum hot film that is coated on a 25 to 150 mm diameter quartz fiber or hollow glass tube. So essentially you create a conducting film on a ceramic substrate. That's what you are doing. So you're coating the ceramic substrate with a metal film. So metal thickness on the film is less than, it is of the angstrom levels, causing the physical strength, and also gives it the thermal conductivity. Okay, so those are the things that you take care when you actually coat the hot wire using this kind of a film. So this is one way of actually doing the hot film anemometry, so to say. So the comparison between the hot film and the hot wire anemometry is that the advantages of hot film over hot wire anemometry is that it has got a better frequency response than the hot wire of same diameter, because the sensitive part of the sensor is distributed on the surface. So it has a low heat conduction to the supports, okay, to the end loss, because it is connected to a frame for a given length to diameter ratio because of the low thermal conductivity of the substrate material, because it is coated on a substrate material. So we can use shorter sensing elements, okay, because that will reduce the measurement volume. So you'll almost go to a point. So the spatial resolution improves. It offers more flexibility in sensor configuration. That means you can make it a wedge, it can make it conical, parabolic, flat surface. This is looks like almost like a tool, like a chisel, but that is this part is what is actually coated with the film. So it is like a wedge that you incorporate in the flow. This is, for example, like a cone. Okay, and this is the normal hot wire type of arrangement. It is less susceptible to fouling and it is easier to clean. Thin quartz coating on the surface resists accumulation of foreign materials. So fouling tends to be a direct function of the size. So all these things, there are certain advantages of hot film anemometry over hot wire anemometry, so to say. So this, if you look at it now carefully, you will see that ultimately it is a heat transfer problem. It is a heat transfer that we are measuring to infer the flow. So that is the crux of this. I mean, it's for each and every measurement technique it is different. Okay.